All right, we're going to end our discussion of algebra-based magnetism by finally incorporating electricity into the mix. So we've done electricity by itself. We've done magnetism by itself. But now it is time to include the and show a case where magnetic fields and electric fields are intrinsically linked in a real scenario and not some weird problem with fields and right-hand rule. So the most natural place that we get this is something known as the Hall effect, which is when you have charges moving in a conductor in a magnetic field with thickness. Because we know that if you do our Q cross B right hand rule, charges in this conductor down here would be pushed down, at least positive charges would. So if there's thickness, of course, these positive charges are going to cluster at the bottom of this slab. So the positives are eventually going to get pushed down here. But the positive charges aren't happy about that, right? Because they're going to electrically repel. So that means that there'd be some sort of electric field in the bar because the positives are closer to the bottom than the top. But those two effects are going to be competing with each other and an equilibrium will be reached. So what ends up happening, of course, this is an exaggerated model, is that we get this sort of crossed fields idea where there's a magnetic field that's trying to push the positives one way and there's an electric field attracting them the other, and these are perfectly balanced. So actually, when you have charges moving in a conductor in a magnetic field, we're going to have these sort of unequal charge densities, which creates a potential difference. So this is known as the Hall effect voltage because you have some sort of potential difference. And this is a very small potential difference, but we'll actually call this just the VBL formula. So if you have a conductor whose width is L, carrying these charge carriers that are drifting at V, we get this VBL is going to be our voltage perpendicular to current flow. So yes, if you have current going through a wire this way, you might have like a positive end of the battery here and a negative end over there. This is actually a voltage perpendicular to current flow. So this is like a secondary type voltage. And it's usually very small because drift velocity is very small. Magnetic fields, those are hard to get large. And this is the width of the conductor. So usually you're going to get small voltages. But what the Hall effect is useful for is it actually tells you what sign of charge is carrying your current. So first, let's verify that before we do some examples. So Hall effect, what we know is that the Hall effect occurs when this like secondary electric field generates a force to exactly balance the magnetic force. So we have these competing ideas. Electric force is QE, magnetic force is QVB. We've actually seen an example of this before where these forces balance in our velocity selector, and the charge actually cancels out entirely. So we can use the idea of like knowing where we want to go with this, that we want to get a voltage. So we know that if there's a uniform field, which we can assume there will be, because we're going to essentially have kind of a capacitor plate idea. And we said the field from a capacitor is uniform when we have these charges on the slab. And this distance is usually not very large. So we can approximate this as a uniform field. We can say that if there's a uniform field, then the magnitude of the potential difference is simply ED. Delta V is ED. So we can multiply both sides of this expression by the length of the slab. And what is E times L? Well, E times L is going to be our voltage that we want. So the Hall effect voltage is VBL. And what's important here is that this L is the direction perpendicular to current flow. There's lots of L's you could use, but this has to be the direction perpendicular, just like with everything magnetism related, that right-hand rule perpendicularity concept. So the voltage is again being probed between these sides, whereas the current is flowing this way. So it's perpendicular to current flow. All right, let's do a couple representative examples here. So we got positive charges moving up through a cylinder, and the magnetic field is into the page. So first we're going to draw the sort of Hall effect setup we have. So if I do QV cross B, My positive charges are going to get slapped to the left. Thumb points up, fingers into the screen, force is left. Now, you could ask, what if, but isn't it negatives that move? That actually doesn't make a difference, because if I do my left hand rule, UV, cross B, negative charges would be slapped to the right. So it doesn't end up working out. So positive charges would get slapped to the left. Negative charges would get slapped to the right. To the electric field, source to sink rule, to that. So what side of the cylinder is at higher potential? Reference your diagram. Well, there's a couple ways of doing it. The easiest way is clearly the left side of the cylinder is at high potential because that's where the positive charges are going. Or remember, we have another rule that says the E field points downhill. So if E is pointing to the right side of the cylinder is at low potential, so the left side must be at high potential. I picked the simple argument. All right, what is the drift velocity of the charge carriers if we probe the sides of the cylinder and got delta? Well, this is just a very simple application of the Hall effect. The Hall effect voltage is VBL. And in this problem, L was the cylinder diameter D. So we get delta V is equal to VB capital D. So my drift speed, V drift, is just going to be delta V over BD. All right, suppose now there's still a current directed upwards, but the charge carriers are negative. This at first should seem confusing. How do you have an upward current, but charges are down? Charges are negative. Well, remember that conventional current is not necessarily the real motion of charge carriers. Conventional current just tells us the way positive charges would move. So one way you can get a current towards the top of the page is totally just having pluses move that way. But remember that sometimes instead of looking at the actual current, we want to just look at, okay, what way are charges actually moving? So you can generate a current towards the top of the screen by having positives move up, but also negatives could move. So if positives would move up to generate this current, it must actually be negative charges moving down if you have negatives generating that. So remember, electron flow is opposite conventional current. So what's the direction of negative charge flow within the cylinder? Down, because it's going to be opposite conventional current. So how will B change? Justify your answer. What is B? That is what side of the cylinder is at higher potential. Well, let's think about what happens here. So if I use my left-hand rule, yes, I have negative charges, but the charges aren't moving up now, they're moving down. And now we see the negatives get slapped left. So that actually changes it, because originally the positives are getting slapped to the left, but now it's the negatives. So we would get the exact reverse. So it'd actually be the same Hall effect voltage if it's the same charge carriers, but it would be the opposite sort of orientation or polarity. Now the negatives would be getting slapped that way. Yeah, I know these cylinders are off. All right, suppose a solution, as I pick up my pen, containing a single type of ion carries a current to the right. I give us our width, but I don't tell you whether the charge carriers are positive or negative. So why is that not enough to determine the sign of the ions? Well, as we saw last time, there's two ways to get a current in a certain direction. One way would be positive charges moving in the direction of current, and the other would be to get negative charges moving opposite current flow. So we actually have two cases here. A rightward current would be generated if I had a positive charge that moves to the right. That's totally a rightward current. But I could also get a rightward current if I had negative charges moving to the left. So in both cases, the current is still pointing to the right, as this tells you the way that positives would be moving. So it's not enough info to tell. So you could either have a positive charge moving right or a negative charge moving left. So it's not enough info yet to be able to tell. So here's why the Hall effect is helpful. Once you start putting magnetic fields in here, the voltage will be a certain sign depending on the charge carrier. So here it says, we probed the top and bottom of the conductor with a very precise voltmeter, and it was measured that the potential difference of the top relative to the bottom is positive 1.5 times 10 to the negative 5 volts. So what that means is that we took a voltmeter like this, and we probed these two ends. And what it says is that this end is actually at higher potential. So there's more positives on the top, there's more negatives on the bottom. We're to use our model here. So this is actually enough info to figure out what charge is being carried. So first we just want to calculate the drift velocity. This is easy. We actually derived this last time. We'll redo it because it's very straightforward. We said delta V from the Hall effect is VL. So the drift velocity is just delta V over BL. The voltage was 1.5 times 10 to the negative 5. And then the B field was 0.05 Tesla. And then I believe the length was also just 0.5 meters. Yep, it was. And this is 6 times 10 to the negative 4 meters per second. So we should look at this, and our reaction should be that is the speed of charge carriers. That's really slow. But remember, this is the drift speed. The electrons are actually moving very fast, or whatever these are. I actually forgot if they're electrons or not. We're going to figure it out. They're moving really fast in there, but they're bumping into each other almost like gas molecules in a container. But they're just slowly being shepherded to one direction by this electric field. So they're progressing really slow on average because they keep bumping into each other, but they are slowly creeping towards one side. So what is the sign of the charge carriers? Well, there's two options. Let's do them both. So what we could do here is we could say, all right, cool. What if we have a positive charge moving to the right? That was one possibility to generate a rightward current, and the B field was into the page. So let's see what's going to happen. Copy paste number 1. And now we're going to see where these positive charges are going to get moved. And of course, copy paste number 2. We're going to do the similar thing for negative. So remember, here are our two cases we're trying to distinguish between. Because you get a rightward current by either having positives move to the right or negatives move to the left. So if we do the positives, UV, using my right hand, cross B, positives would be slapped upwards. So positives would be slapped upwards, meaning we would get this scenario. What about negatives? Well, for negatives, I use my left hand, UV, negatives are moving left, cross B, negatives are getting slapped upwards. And this is totally enough info to figure it out, because the charge carriers got pushed to sort of the same side of the slab. So the voltage is enough to tell, because the Hall effect voltage wasn't just a number, it was a signed number. So this was the scenario we got, where the positive end was actually the top of the slab, and the only way that could happen is if our charge carriers were positive. So delta V top was larger than delta V top was larger than in our experiment according to that number, which is consistent with positive charge carriers. So this is why the Hall effect is helpful, because the Hall effect, it really helps you distinguish between the two. So this is how you could definitively tell what is carrying the current in your circuit. Is it positive or negative charges? We'll just do a Hall effect experiment, because this is how you can totally distinguish which charge is which. That's kind of a cool little thing. Now, when we talk about the Hall effect, we can actually use it to complete a circuit in this effect known as the bar on rails problem or motional EMF. This is like the scenario to know. We love our bar on rails problem. What's happening here is we have a conducting bar that's connected to a light bulb of resistance R, and it's pulled by an external force across a set of U-shaped rails. So the rails are completed on one side, and this bar is being pulled by an external force to the right. So first, because this is in the section with the Hall effect, this is actually a Hall effect problem. So what is happening to the conducting bar as we move it to the right in this B field? Well, it doesn't matter what the charge carriers are, because we'd get the sign correct either way, because we're just talking about the motion of charge carriers. We're not talking about current or anything, right? So if my positive charge carriers in the bar are moving to the right, because the velocity is to the right, and the B field is at me, so the positive charges are getting slapped down. So I would be getting positive charges that are down and negative charges that are on the top. Now, you could just as easily pretend that it was negatives in there that will be doing the moving. So my left hand, it's there, and then up. So negatives get pushed up. Same idea. So it's easier just to use your right hand rule for this. It's the same either way. Just remember, if you're pretending it's the negatives that move in your example, just pick the left. All right. So due to this, there's going to be some sort of enforced separation happening where, yeah, the charges are separated. And since charges are separated by force and they're not allowed to connect to each other, you have a battery. That's entirely what a battery does. So what this means is that this is no longer a conducting bar. This is actually a little mini battery. So we can actually draw our U-shaped rails as some circuit with a battery in it. So we have our light bulb, and then we have our conducting bar. So I'm going to erase this in a second. But there's our conducting bar. But what we said is that our conducting bar is really a sort of battery, with the positives being at the bottom end and the negatives being at the top end. So what we can do is we can just replace this with a battery. Because, again, a battery has a positive end and a negative end. So what is that going to do? Well, we know that current is going to actually start to flow. We have a completed loop. So it's not just the Hall effect where we have a voltage, but we have a loop. So we have a voltage that sort of connects back on this loop. So we actually do get a current that's going to flow, and this is going to be clockwise. No, yes, clockwise. Hardest part, man. Hardest part. Counter or regular clockwise. So we get a clockwise current. So just by moving this bar in this magnetic field, due to the Hall effect, we actually get current. So this is creating current without a battery, which we've needed in all of these cases. We've needed some sort of battery to supply a potential difference in our circuit. What is the current passing through the bulb? Well, what is current? We have a circuit now, so we just use our good pal, Ohm's law. Current is EMF divided by resistance. And we do actually know what the EMF is. The EMF is being supplied by the Hall effect. And the Hall effect voltage is VBL. So our current is VBL over R. Which makes sense, because the faster I pull that bar through the B field, that's going to create a stronger separation, so I get a stronger driving voltage. What is the power dissipated? Pick your favorite. Pick your favorite power formula. We have 3 power formulas. Definition: power is the charge per second times the amount of energy per charge, which would be energy per second. Or doing some Ohm's law substitutions, you could get I squared R, or not centripetal acceleration, delta V squared over R. We have both here. Let's just use I delta V. I was VBL over R. Delta V is the Hall effect voltage, VBL. So we get 2 copies of VBL. So we get VBL quantity squared over R. And that should be pretty clearly the 3rd power formula, right? Where we see a squared voltage. All right, derive an expression for the magnitude and direction of the magnetic braking force acting on the conducting bar due to the current. So what does that mean? Well, remember, there's a bill force that's going to act on this because now we have current. So now we're going to go back to just modeling the bar as an actual bar, just to help us make sense of what's happening here. So remember that now we actually have current, and we said that the current is going clockwise. Nope. Yes. Man, did it again. So this means that our current in the bar is going to be going down because our current isn't just going to magically change direction. And we also said that there's a B field in this problem that points out to the page. So if we do that, we can do our QV cross B now. So now we're actually looking at the current within the bar. So this is a different magnetic force than the individual charge carriers. They're being pulled this way. We're sort of looking at the actual induced current. So we do QV cross B. That's to the left. So we actually get a magnetic force, and this is why it's actually called a braking force. It is always this case that in these types of problems, the magnetic force, the bill force, will always fight whatever direction the motion is going in. And that's a consequence of something called Lenz's law that we're going to talk about. But it's actually always the case, and you don't need to go through this argument ever again. It's always going to be the case that in these scenarios, the magnetic force on these bars is going to oppose the motion. So what is bill? So we know that it is the bill force, BIL. But we actually just found I. I was EMF over resistance, which was VBL over R. So we get 2 copies of B, 2 copies of L, 1 copy of R, and then V. And this was to the left. And I actually put the V out in front to show you that this is sort of a drag force. It's actually a force that's proportional to velocity. Because the faster you pull, the more current you get, so the larger bill you get. So actually, this is a drag force. So if we were to let go, our bar would be sort of slowed to a stop in a drag force style problem. Using the fact that the bar is traveling at constant velocity, determine the magnitude of the applied pulling force. Oh, well, that's really easy. Because all we're saying is that, yeah, if this bar is moving to the right, it's going to be experiencing a magnetic force. Well, if it's moving at constant velocity, you must be pulling it exactly with the same force the other way. So F pull going to be equal to the bill force. And we said that was equal to B squared L squared over R times V. Cool. Using the fact that power equals force times velocity, verify that the rate of energy input by the external force is equal to the rate at which energy is dissipated by the bulb. So this is a mechanics idea. It's sort of just manipulating power as work divided by time, because you get work is FD over time and D over T is V. So this is a just clever manipulation of work formula. So power in is equal to the power of the pulling force which is just equal to F times V, which is equal to V squared L squared over R times V. And notice what that does is that gives us another V. So we get BLV all squared divided by R. So that's power in. And that is actually the same thing we got, because we actually, if we scroll back, what our power out is, our rate of energy out of the circuit is power dissipated by the bulb, which was equal to EMF squared over R. And we said the Hall effect voltage is the EMF VBL, which we could also write as BLV. So, very cool. Energy is conserved. The energy that goes in from the force is converted into heat and light from the bulb. Very nice. So this is a pretty significant problem. This is our first sort of connection between electricity and magnetism that isn't some contrived right-hand rule field balancing problem, where you can actually create a current just by moving a bar through a magnetic field. So by moving something through a magnetic field, you can create a current. That's a pretty significant result. So moving a conducting bar on rails through a magnetic field generates electric current. Current will flow through the loop, and there's also going to be a magnetic force resisting the bar. So you can't do it for free. Like, you can't just pull it and let it go. You're going to slow to a stop. So you have to be putting in energy to sort of fight Bill. So this is generally called motional EMF. And this can also be understood in the concept of one of the very important equations of E&M, Faraday's law. Faraday's law says if you change flux, which is BA, that pierces a loop, you will induce an EMF. So this is a special case of Faraday's law, which is a fundamental equation. It's actually one of the 4 Maxwell equations that fully describe E&M, because this is super important. It's an equation that connects magnetic flux to EMF, an electric quantity. And also, there's a little corollary of Faraday's law, which is known as Lenz's law, that says not only do you get an EMF/current by changing flux, but the current is going to be directed in such a way to fight the change in flux. Because remember that currents generate magnetic fields. So if your flux is going to increase, maybe you get more circles, more out of the page flux sort of coming at you, then your current would have to be induced in such a way to generate an into the page flux to fight it. Now the Hall effect will totally work for figuring out these things in the motional EMF case, but also it's nice to actually verify this. So, for example, if you just try to do B from a wire in the case of a circle, you'll see that you get this idea where if you have a counterclockwise current, you get a B field that points at you. And if you have a clockwise current, you get a B field that points into the screen. And notice, like, if I try to just align my finger with these things here, with these little tangent arrows for the current, notice if I wrap my fingers around the loop at each of these times, my fingers are always going to pop out of the page if I'm going clockwise, and they're going to point into the page, or sorry, counterclockwise is out of the page. And if they're clockwise, my fingers are always going to pop into. Wherever I try to grab the loop, my fingers curl if I'm going. So that's just a consequence. All right, so here's the other motional EMF case to know. So we like the bar on rails problem because it's more real than this. This is our magical conducting loop that is marching into a B field. We're just gonna not ask questions how that happens. So first, we're gonna consider a time where this conducting loop is partially in the field. So we're gonna justify why there's gonna be current using the Hall effect, and then this newly mentioned Faraday's law, which talks about flux. So first, the Hall effect. This is actually identical to the problem we did earlier. So why is there an EMF induced in the loop referencing Hall effect? Well, Hall effect, I'm moving to the right, and my charge carriers are moving to the right, and my B field is out of the page. So I'm going to point down. So that means that there would be positive charge carriers there. So my positive charge carriers are pushed down. So why is there an EMF induced in the loop referencing the Hall effect? Well, this essentially creates a little mini battery like this. So we get a little mini battery, and again, it's only that side of the loop. There's no magnetic field here yet. So we only get a little mini battery on the right side. We'll scoot this. Positive charge carriers will be pushed towards the bottom of the bar, creating a potential difference. Why is there an EMF induced in the loop referencing Faraday's law? So Faraday's law is about flux. And again, remember, flux is the amount of magnetic field that pierces the area. So why is there an EMF according to Faraday? Well, notice that as I'm moving to the right, there's more B field that's sort of piercing this area. So I'd be shading more and more of this area of the loop with B field as I get closer and closer. So the magnetic field is out of the page, and it's penetrating an increasing area of the loop. Because imagine, as I'm marching into this field, I'm sort of getting more circles with time. Because as I march towards this field, more and more of these circles are going to pierce the square until I'm all the way in. So we do actually get a flux change, because flux is equal to B perp times A, and it's entirely perpendicular. So we're just marching in and getting more and more flux. All right, what's the direction of induced current? Justify using Hall effect. That's really easy with the Hall effect, because we already drew our circuit. That's not what I hit paste instead of copy. So here, the left end, on the left side of the bar, the bottom end is at higher potential, so we get a clockwise current, right? What do I mean by that? On the left side of the bar, bottom end is at, I don't think I need that. The bottom end is at higher potential, causing current to flow clockwise. All right, now we have to justify it using Lenz's law. So this is the more subtle one. So this is how I always like to think about Lenz's law. So remember, Lenz's law says if there's a flux change, it will the induced current must generate a B field to fight the change. So if I'm marching my loop into the B field, I'm getting more circles, more circles, more circles. The field is coming at me. More circles are piercing the square. So Lenz's law says I need a B field that doesn't generate circles, because Lenz's law is sort of like a restoring force idea, where the loop is very unhappy that you're increasing the circles through it. So what has to happen is you have to generate a B field that generates X's. So that current is going to generate X's. So how do we do that? Well, if we wrap our fingers around, we see that that is clockwise, as expected. To oppose the increase in out of the page magnetic field, a clockwise current is induced to generate an into the page B field. Because if we draw a current that goes clockwise, that generates a B field at the center of the loop that would be into the page, trying to cancel the circles. Now let's look at the other case where we're fully inside the B field. Why is there no EMF justifying the Hall effect? Well, we said earlier that the Hall effect says that in this case, positives get pushed down, negatives get pushed up. But the main difference here is now there's two sides of the loop that actually experience this Hall effect. So what does that do? Well, if we look at our new picture, we actually get like a double battery circuit where we'd get this. So what does this do? Nothing. The currents are going to fight each other. So if this battery outputs a current this way, this battery outputs a current this way, they're going to cancel. So we actually get canceling sort of currents, or canceling EMFs in this case. Charge carriers are separated on both sides of the loop. Induced EMFs will therefore cancel. Now, what about Faraday's law? This is actually easier to justify with Faraday's law because notice that as my loop is marching through the field now, there's no change in circles. Whole B field, the whole square loop is penetrated by the B field. So there is going to be no more flux change. When the loop is fully in the field, there's no flux change, so we get no EMF. That's what Faraday says. Right? It just marches forward. And no flux change, no EMF, no induced current. So here's the formula for motional EMF. So if your flux is changing, you can apply this formula. The Hall effect works when flux is changing. And it reduces to that same result we saw. And because this is a non-conservative electric field, and there's some subtleties there, we usually don't call this a voltage. I'm not the greatest at checking my language there, but we'll usually call this EMF and not voltage. It really doesn't change anything for us, though. And the two main cases of this is first we have the magical conducting loop marching field, and the second one is the bar on rail problem. So if you have a change in flux, you get a VBL Hall effect voltage. And if you are fully in the field, you have no flux change. So you don't get an induced EMF. Well, technically you do, you just get two sort of canceling EMFs. So let's do a ranking task to really test our knowledge here. So we have 4 loops. They each have the same resistance and have the same speed and are moving through the same B field. They just have different dimensions. We're going to rank the current induced in each loop, and then we will justify it. So, of course, we're ranking current. So what is current related to? Well, we know that current is going to be EMF divided by resistance, and EMF is the Hall effect voltage, VBL. So let's see what's going to happen in each of these cases. So case 1, this is just our standard Hall effect. We've right-hand ruled this exact scenario a few times. We'd get positives pushed down here, negatives pushed up here. We do get a Hall effect net voltage because only one side of the loop is there. We're entering, so we are getting a flux change. So this EMF is going to be VBS. All right, what about loop 2? Same idea, plus plus, minus minus. I have a longer loop. Does that matter? Actually not, right? Because the Hall effect voltage is about this length. How long have you separated the charges over? It's still S, so this is actually the same EMF, VBS. All right, what about loop 3? So same idea, plus plus, minus minus. But now my loop is twice as long, but in the other way. So now I actually do get a different EMF because I'm separating the charges over a bigger distance. So that E field is over a larger distance. So this is actually VB2S or 2 VBS. And then lastly, loop 4, I'm fully in the field. So actually I get no flux change, so I know EMF is 0, or I get the double Hall effect canceling batteries, so EMF is 0. So if we were looking at our results here, we get VBS for the first 2 VBS for the third one, and no EMF for the So induced current is going to be the least in case 4 or D, 4. Least in 4. We have a two-way tie at 1 and 2. And then we have a greatest at 3 because we said this was 0. This EMF was VBS, and the greatest was 2 VBS. And again, I know that it asks about current, but this is just related via Ohm's law, so we can rank the EMF. In loop 4, there's no flux change. We're fully in the field, so there's no EMF. Loops 1 and 2, the length of the loop of which charges are separated is the same. So there's a non-zero equal EMF induced. Because yeah, one of the loops is bigger, but we have separated them over the same distance, the charges at least. Loop 3 has charged the length, twice the length where charges are separated, so we get a higher length. And again, the reason we could do this and just rank the EMFs is because they had the same resistance R. And that's actually not going to be the case in this last one, where we have a really tricky ranking. This is more of an extension activity. Suppose instead they don't have the same resistance, but the same resistance per length, which is a much more reasonable assumption. So now we actually have to kind of incorporate this. So what we learned before is that 1, the EMF was VBS. 2, the EMF was VBS. 3, the EMF was 2 VBS. 4, the EMF was 0. So now we actually have to incorporate the length of these loops into the equation, because the more length you have, the more resistance, and that's going to be a linear relationship, same resistance per unit length. So let's do each of these. So what we want here is the total length, or the perimeter, of each of these 4 loops. So loop 1 is an S by S square, so that's SSSS, which makes 4S. Loops 2 and 3 are going to be S by 2S, so that's SS, 2S, 2S, which makes 6. And the other 2 are also the same dimensions. So we'd get your perimeter, you were just the 1 by 1, so that's 1 times 4, so that would be S. And then these perimeters were all 6S, because you had 2 2s and 2 1s. So how can we rank the current here? Well, first of all, it's easier to figure out who loses, because there's still no current here. Then we're really just sort of dividing these 2 quantities, right? Because if the resistance per unit length is the same, so this makes an effective current. This makes an effective current of 1/4. This makes an effective current of 1/6. This makes an effective current of 2/6, which is 1/3, and you're of course. And we'll talk about how you could have done this qualitatively in a minute. So actually notice that now we no longer get a tie at 1 and 2, because yes, 1 and 2 have the same EMF, but loop 2 actually had more length, so it had a larger overall resistance. And 3, yes, it had double the EMF, but it actually didn't have double the length as the original, because you only increased 1 side length. So we actually still get a net winner in the loop 3 case. So we could have done this conceptually by realizing that 4 obviously loses, because it has no current. 1 and 2 have the same EMF, but 2 has a longer length. So we know that 1 has more current than 2. But also we know that 3 should still win, because 3 has double the EMF, but it doesn't have double the perimeter as the others. So that's why we could have done this. Really hard though. Like, this is not an easy ranking by any means. And now we will finish. I say we'll finish with one problem, but this is quite an involved problem with many subparts. We have the more interesting variation of the bar on rails, which is the bar on rails with no force pulling you. So instead of being pulled, we're being just launched and let go. And we said in that case, we get this sort of magnetic drag force that just wins and will eventually stop your bar. So indicate whether the magnitude of the bar's acceleration increases, decreases, or stays the same after we release the bar. So we're essentially asking, is the rate at which the bar is slowing down, does that change, or is it constant? Now, if you know anything about drag force, you might remember that drag force is not uniform acceleration, because it depends on V. So the math explanation is that we know we're going to get some sort of a drag force. We know for sure that Bill always fights the change, because that's a Faraday's law, Lenz's law effect, right? The Bill force is going to try to oppose the flux change and pull you backwards into where you came from. So we know that the force actually is going to decrease, because you get strongest drag when you have the strongest speed. So since the speed is slowing down, the drag force is going to decrease, so acceleration is going to decrease. So we actually do know that the acceleration will decrease, because in this sort of drag force related problem, you get a strongest force when your V is the highest. So how can we reason through this qualitatively without really needing the drag idea? So we do know that the net force is Bill. But what is affecting the Bill force? Well, Bill we also know that this is a motional EMF problem. So we have an EMF that's equal to VBL. And we also know current is EMF over resistance. So all of these things are qualitative facts that we can use together. Now, if we start plugging them into each other, that's the realm of derivations. But realize that your bar is going to slow down. So if your bar slows down, that's less speed. You have less speed, you have less EMF, you have less current, so less Bill, so less force, so less acceleration. That's a huge chain of reasoning here. The acceleration of the bar is caused by the braking force, which slows down the bar. This force depends on induced current, and since induced current increases with velocity, the braking acceleration is greatest initially when the bar is at highest speed. So as the bar slows down, its acceleration is going to decrease because the Bill force is going to decrease. So what is the acceleration? Well, we want acceleration. So, of course, we know that acceleration is given by Newton's second law, F net divided by m. So what is F net? Well, F net, I always like to define F net as things helping the motion of the bar minus things hurting the motion of the bar. And the motion of the bar is to the right. Is there anything helping the bar to the right? Nope, because this is not a problem where we're pulling it. So there's actually just the Bill force. So I have nothing helping and the Bill force hurting. All right, now we start our substitution frenzy here. So what is the Bill force? Well, what is current? Current is, of course, just EMF over resistance by Ohm's law. Okay, and I think we're going to run out of space, so we'll do it here. And what is the EMF? Well, this is the Hall effect / motional EMF formula, just VBL over R. So now we can simplify and we get that result we actually got in the first problem. So we actually see that our F net is going to be due to the Bill force, and that's negative V squared L squared over R times V. So this means that our acceleration is just going to be the exact, that exact thing, but divided by m by Newton. So Newton's second law says we get acceleration by just tacking on an m in the denominator. So we get v squared L squared over mr times v, and that is oriented to the left. So is that consistent with our claim? We claimed that as this bar slows down, its acceleration will also decrease. Absolutely, right? Because notice what's in this expression for acceleration. Acceleration depends on velocity. So for those of us with some calculus experience, you can actually see how this is eventually going to turn into a differential equation we can solve in our calculus-based unit. So is it consistent? Absolutely. Acceleration is proportional to velocity, which makes this a drag force. And since the speed of the bar is decreasing, the acceleration of the bar will also decrease, consistent with part A. All right, so now we're just asking, what is going to be the total energy dissipated by the resistive load after a long time? So there's a really hard way to do this. A hard way to do this would be to say that power is equal to EMF squared over R, which is V squared, B squared, L squared for R. But here's the problem. We don't know V. We don't know V for the bar. We know V is initially V0, but we don't know how V varies with T. And then we'd have to end up doing some sort of integral idea and a bunch of calculus to do this. But what can we do since it's an energy problem? Well, since it's an energy problem, we can do conservation of energy. So total energy dissipated. So this makes us think about total. So we're going to use conservation of energy. Use energy. And why can we do that? Well, notice that nobody is putting energy into this system. It's all being removed. So after a long time, this bar is going to be completely stopped by the magnetic force. So what that tells us is that all of the energy of this bar is being stolen by this resistor in the form of heat. So what that means is that all energy from the bar is eventually dissipated. So this means E total is just going to be the initial kinetic energy of the bar, which is 1/2 mv squared. Now, I think it's fun. People would disagree with me. There's a crazy expression you get for the V. Like, if you do this for V of the bar, you'd actually solve like a differential equation and you get this nasty expression for the speed of the bar as a function of time. And if you plug that into a power formula and integrate from 0 to infinity, you do get this. It's really cool. It's a really cool problem to actually verify that if you do the power formula with motional EMF with that function, you actually do get that it's just the kinetic. But energy conservation is always clever. All right, and then the last variation of the bar problem we'll look at now is the same problem, except you drop the bar along the rails and it's a vertical problem. So now we're going to incorporate gravity. So what's going to happen? Well, initially, it says justify why the bar will reach a maximum speed by falling. That's actually our first part. So right when I drop the bar, it's going to experience some gravitational force mg. What's that going to do? Well, of course we know what it's going to do. The bar is going to be in free fall initially. So the bar is going to be in free fall at that instant, and then it's going to start moving. That stays the same, of course. So what does that do? Well, now my bar is moving. And if I have a moving bar in a magnetic field, we're going to have a braking force. So now the braking force is going to fight motion of the bar. Okay? But gravity still wins, right? Our gravitational force is still going to win. Like, yeah, I have a little bit of a drag force, but we're still going to be moving down and accelerating down, meaning my speed is going to increase. What happens if my speed increases? And Bill increases. And Bill can increase until eventually they balance. So this actually gets terminal velocity. So this is like literally a drag force problem where you have terminal velocity, because after a long time, and I think I'll move this up and shrink it a bit so I can just make it a column here. So after a long time, it's going to reach some terminal speed. So it's going to be a much larger speed, the terminal. And why is it called terminal? Well, again, you still have your same old mg, but eventually, after a long time, your magnetic force got big enough due to the large speed that that drag force is finally big enough that it exactly balances the gravitational force. So we start with no magnetic force, then it gets bigger and bigger and bigger and bigger, and it eventually cancels out. So initially, the bar is not moving, so it's accelerated downward by gravity. As the bar speeds up, the braking force increases, and eventually these forces balance, causing terminal speed to exist. Terminal meaning maximum, right? Because what happens if it went faster than that terminal speed? Well, then the magnetic force would win and slow you down to that magical matching speed. It's actually really easy to get the terminal speed of the bar now, because we know that FB and FG balance each other. FB, we worked out in the previous problem. I don't think we need to redo it. And mg is the gravitational force. So we worked this out in the previous problem, that the magnetic force acting on the bar at velocity v could be written as this expression. And again, it's because B is Bill, I is EMF over resistance, and EMF is the Hall effect. Cool. So what is V terminal? Well, V terminal would just be send everybody else to the other side. So we'd get mgr which looks like a torque, but it's not, divided by B squared L squared. We can do a quick sanity check on this before we call it a day, in a unit actually, because if I have a more massive bar, I'm going to have a higher terminal speed, which makes sense because I have more inertia. So it would take more magnetic force to balance me. That's why G is there too. R makes sense because if you have a bigger resistance, you get less current. You have to go faster to get the balancing current. And B and L go on the bottom. That makes sense because if you have a stronger B, you have a stronger braking force. And if you have a stronger L, a larger L, you get a stronger battery. So you get a larger. All right. That is our algebra-based magnetism unit complete.